In the middle of the ocean, an aircraft carrier prepares to launch another group of fighter jets. Dozens of aircraft line up across the deck. One after another, they accelerate to incredible speeds and disappear into the sky within seconds, even though the nearest land base may be more than 1,000 kilometers away. But an aircraft carrier cannot simply stop in the middle of the ocean. Without a powerful source of energy, the ship would slowly lose its ability to move, launch aircraft, operate its radar systems, and support the thousands of people living on board. At first, the solution might seem obvious. Why not install enormous diesel engines, just like those used on most civilian ships? But deep inside the hull, something far more powerful is operating. Several nuclear reactors work continuously beneath the carrier's armored decks. For years, these reactors can generate an enormous amount of energy without requiring conventional refueling. They power the ship, drive its massive propellers, operate advanced military systems, and provide electricity for what is essentially an entire floating city. But the most surprising part is that nuclear fuel is not the only reason these ships use reactors. The real explanation is much more important. In this video, you will discover why aircraft carriers rely on nuclear power.
Complete calm in the open ocean can be one of the worst situations imaginable for the commander of a conventional aircraft carrier. Picture a steel island weighing more than 45,000 tons. It is completely motionless in the middle of an ocean that looks like a giant mirror. At that exact moment, one of the first powerful jet fighters is preparing for takeoff. Its engine roars across the flight deck. The pilot pushes the throttle to maximum power. The launch system activates. The heavy aircraft races toward the edge of the carrier. For a brief moment, everything appears normal. Then the aircraft reaches the end of the deck. But instead of climbing into the sky, it falls. The enormous machine drops like a stone and disappears beneath the ocean waves. This is not a scene from a movie. It is the result of cold and unforgiving physics. During the middle of the 20th century, the arrival of powerful jet aircraft created a serious problem for naval engineers. The new aircraft were much heavier than older propeller-driven planes. Their engines produced enormous power, but their wings also required much more airflow to generate enough lift. Without a strong wind blowing directly across the flight deck, a fighter weighing tens of tons may not have enough airspeed to remain in the sky after leaving such a short runway. That means an aircraft carrier cannot remain still. It has to run. It must move as fast as possible directly into the wind. The ship may need to reach speeds of more than 50 kilometers per hour. At full speed, the massive steel hull.
History recorded a clear example of this problem when a massive American aircraft carrier entered an area of almost complete calm. The ocean became perfectly smooth. There were no waves. There was almost no wind. The surface looked like a sheet of glass stretching endlessly toward the horizon. To create even a small amount of airflow above the flight deck, engineers deep inside the ship pushed the steam turbines close to their limits. The boilers became extremely hot. Mechanical systems operated under enormous pressure. The carrier consumed fuel at an alarming rate. Hundreds of tons of fuel could disappear every hour while the ship attempted to maintain maximum speed. But even that was not enough. The aircraft had become heavier, and the available airflow still could not provide a safe launch. Eventually, the command was forced to stop all flight operations. One of the most powerful military airfields in the world had suddenly become a helpless steel island. This revealed a serious weakness. A conventional aircraft carrier traveling at maximum speed becomes an extremely hungry machine. Its fuel tanks begin emptying at a frightening rate. If a diesel-powered or oil-powered carrier is forced to remain at maximum speed to support continuous aircraft operations, its enormous fuel reserves can be exhausted within only a few days. Then the ship faces a dangerous possibility. It may be forced to slow down or stop in the...
Imagine two enormous steel ships traveling through a violent ocean. They move only around 30 meters apart. Massive waves push both vessels from side to side. Their huge hulls rise and fall as the ocean crashes against them. Between the ships, thick steel cables remain under constant tension. Heavy fuel hoses stretch across the narrow gap. Thousands of liters of fuel are transferred while both vessels continue moving. One incorrect steering movement could create a disaster. A sudden change in the wind could push the ships closer together. A powerful wave could force one enormous hull directly into the other. If that happened, thousands of tons of steel could collide with tremendous force. Metal could tear apart. Fuel lines could break. The entire operation could become extremely dangerous within seconds. Navies call this process underway replenishment. And for a conventional military ship, it can be one of the most vulnerable moments during an operation. A traditional oil-powered aircraft carrier must experience this situation again and again. Every few days, its commander may be required to reduce speed, move into a dangerous parallel position, and remain connected to a supply tanker. During this time, the carrier loses much of its freedom. Its ability to maneuver quickly becomes limited. It cannot immediately turn away from danger. And if an enemy is watching, the carrier may become easier to locate and predict. Imagine trying to drive across a massive desert where there are no gas stations. To avoid running out of fuel, you decide to pull an enormous...
In July 1964, American Rear Admiral Bernard Strain decided to demonstrate that the era of oil-dependent naval fleets was coming to an end. He led an extremely ambitious operation known as Operation Sea Orbit. The mission was simple to describe, but incredibly difficult to achieve. 3 modern nuclear-powered warships would leave port and travel around the entire world without stopping to refuel. At the center of the fleet was the enormous nuclear-powered aircraft carrier USS Enterprise. The ships carried enough nuclear energy to continue operating without depending on conventional fuel tankers. The journey lasted 65 days. The nuclear fleet traveled more than 55,000 kilometers at high speed. It crossed several oceans. It passed multiple continents. And during the entire operation, the ships did not enter a single port to refuel. They also ignored the traditional supply vessels that conventional fleets depended on. The mission demonstrated something extraordinary. Nuclear power allowed a military fleet to operate far from the coastline without being constantly connected to fuel supplies. The ships were no longer controlled by the location of fuel tankers. They were no longer forced to stop because their engines had consumed too much oil, and they could remain at high speed for much longer periods. But nuclear power created another important advantage. Traditional aircraft carriers required enormous internal tanks to store millions of liters of fuel.
Imagine that you are a fighter pilot returning to an aircraft carrier late at night. Below you is nothing but the black ocean. There are no city lights. There is no visible coastline, only darkness. Far ahead, a small illuminated flight deck appears in the distance. You carefully maintain your speed. You remain perfectly aligned with the landing area. Only a few seconds remain before your wheels touch the deck. Then, something invisible strikes the aircraft. The fighter suddenly drops several meters. The instruments begin reacting unpredictably. The wings rapidly lose lift. The aircraft shakes violently. You have entered a dangerous area of unstable air created by your own ship. The source of this problem is hidden inside the enormous exhaust system of a conventional aircraft carrier. Diesel and oil-powered engines continuously burn huge amounts of fuel. The engines release enormous volumes of extremely hot exhaust gas. The temperature of the exhaust can rise above 300 degrees Celsius. Massive streams of hot air move upward from the ship's exhaust structure. And sometimes, these gases travel directly into the path used by aircraft approaching the deck. According to the laws of physics, hot air is less dense than the colder air surrounding it. This creates unstable areas of turbulence. Behind the carrier, the airflow can become unpredictable. The pilot may suddenly encounter a region where the aircraft loses.
In 1960, the French Navy introduced the aircraft carrier Clemenceau. Engineers already understood that hot exhaust gases could interfere with aircraft landing operations. They attempted to solve the problem by installing a large curved exhaust structure. The design was intended to direct smoke and hot gases away from the landing area. At first, the solution appeared promising, but later, newer and more powerful jet fighters began operating from the ship. The problem returned. Pilots continued experiencing severe turbulence while approaching the flight deck. One pilot later described how his aircraft seemed to fall into invisible pockets of air immediately before landing. The hot gases did more than shake the fighter. They affected visibility. They created powerful distortions in the air. In some conditions, the exhaust could irritate the pilot's eyes, even through protective equipment. During those final seconds, the aircraft could become difficult to control. One small mistake could result in the loss of the aircraft. The French Navy was forced to establish strict operating procedures. The carrier sometimes had to reduce engine power while recovering aircraft. But reducing power created another problem. The ship needed speed to generate airflow across the deck. Now the engineers faced two competing requirements. The carrier needed powerful engines to support aircraft operations, but powerful conventional engines created more exhaust turbulence. There was no simple solution. Building a larger exhaust system would increase the size of the ship's structure. It could also make the carrier easier to detect. The hot exhaust created a strong thermal signature. Enemy sensors could potentially detect the heat from a great distance. The exhaust system reduced the ship's ability to remain hidden. But nuclear power offered a completely different design.
Imagine sleeping peacefully inside a small cabin. Only around 50 meters beneath your bed, a controlled nuclear reaction is producing enormous amounts of heat. Temperatures inside the reactor reach hundreds of degrees. The reaction continues day and night. You remain on board for months, yet you are completely safe. This is not science fiction. It is normal life for sailors serving aboard a nuclear-powered aircraft carrier. Nuclear engines have always been surrounded by frightening stories. Many people immediately imagine dangerous radiation spreading throughout the ship. But the real safety systems used inside naval reactors are far more complex than most people realize. One of the most important figures behind these systems was the legendary American Admiral Hyman Rickover. He became known as the father of the United States nuclear navy. Rickover was famous for his extreme attention to detail. Some people described his approach as almost obsessive. He demanded extraordinary reliability from every component. He personally examined reactor systems. He closely monitored the training of naval officers. He believed that nuclear technology could only remain safe if every person involved understood the consequences of even the smallest mistake. Historical accounts describe Rickover spending long periods near the protective barriers of early naval reactors during testing. He personally remained close to the control systems during important stages of the first nuclear operations. His goal was to demonstrate confidence in the technology. But the safety of the reactor did not depend on confidence alone. It depended on layers of powerful physical protection. The entire system can be compared to an extreme...
At the center of the nuclear reactor is the active core. This is where uranium fuel produces heat through a controlled nuclear reaction. The core is sealed inside a massive steel pressure vessel. The walls are extremely thick and designed to withstand enormous pressure. Around the steel structure is a large volume of purified water. The water performs several important functions. It transfers heat away from the reactor. It also absorbs many forms of radiation. Outside this system are additional protective materials. Heavy shielding and strong armored steel surround the reactor compartment. Together, these layers form a powerful protective barrier. The system works like several shields placed one behind another. The reactor is not exposed directly to the crew. Its energy remains contained inside multiple engineered structures. Measurements performed aboard nuclear aircraft carriers produced surprising results. A sailor serving on a nuclear-powered ship may receive less radiation during a year than an average person receives while living in a large city. At first, this may sound impossible, but there is a scientific explanation. People living on land are continuously exposed to natural background radiation. Cosmic rays arrive from space. Certain rocks and building materials release small amounts of natural radiation. Even the ground beneath cities contributes to the total exposure. On an aircraft carrier, the enormous steel structure provides protection from some forms of cosmic radiation. The ocean surrounding the ship also acts as a natural protective barrier. Admiral Rickover created extremely strict inspection and operating standards.
Throughout the history of the naval reactor program he developed, the safety record remained remarkably strong. The nuclear reaction became a controlled source of energy. It was no longer an uncontrollable force. But safety was only the beginning. Modern aircraft carriers require an unbelievable amount of power, and conventional diesel generators cannot always.
Imagine an entire modern city. Factories operate continuously. Homes consume electricity. Hospitals run advanced equipment. Streetlights illuminate thousands of roads. Transportation systems remain active. Now imagine compressing much of that enormous infrastructure into a single military ship. This is not an exaggeration. It represents the scale of energy consumption aboard a modern nuclear-powered aircraft carrier. One enormous carrier can require an amount of electricity comparable to that used by a large industrial city with a population of around 100,000 people. And that energy is not used only to rotate the massive propellers beneath the hull. A modern aircraft carrier is also a powerful military information center. Advanced radar systems are installed across its upper structures. These electronic systems scan enormous areas of the sky and ocean. They can monitor hundreds of targets at the same time. The carrier must continuously process large amounts of information. Its radar systems require a stable and uninterrupted supply of electricity. Imagine a normal apartment building where thousands of powerful electric kettles, heaters, and washing machines are switched on at the same moment. The electrical wiring would quickly overheat. Safety systems would activate.
Nuclear energy does more than operate the carrier's engines and radar systems. It creates opportunities for future military technology. Modern warships are already testing powerful defensive laser systems. Engineers are also developing advanced electromagnetic weapons. These systems may require enormous amounts of electricity. Some need a massive burst of energy within only a few seconds. A conventional diesel generator may not be capable of producing that amount of power instantly, but a nuclear-powered ship can support much larger electrical systems. The reactor provides a continuous source of energy. Large electrical storage systems can collect and release that energy when needed. This could allow future carriers to operate weapons that require enormous electrical pulses. Nuclear power transforms the aircraft carrier into something more than a floating airport. It becomes a powerful mobile energy platform. The ship can operate advanced radar. It can launch aircraft. It can support thousands of people. And it may eventually operate energy weapons capable of defending the entire fleet. But there is a major cost. Building a nuclear aircraft carrier requires an extraordinary amount of money. Operating one is even more difficult. The reactor must be inspected. The ship requires specialized facilities. Thousands of highly trained engineers and technicians must remain available. And eventually, the nuclear fuel must be replaced. That process creates one of the most complicated engineering operations ever performed on a military ship.
Imagine standing beside a steel island weighing more than 100,000 tons. Deep beneath its armored flight deck is a nuclear reactor. The reactor is surrounded by thick layers of steel and protective shielding. Now imagine being asked to remove the used nuclear fuel from the center of that enormous ship. How can engineers reach the reactor? How can they remove radioactive fuel safely? And how can they complete the operation without turning the naval base into a dangerous restricted area? The solution costs billions of dollars. Only a small number of countries possess the technology and infrastructure required to perform the work. Admiral Hyman Rickover established extremely strict standards for nuclear reactor personnel. He personally conducted difficult interviews with many future officers. He demanded precision. He expected complete understanding of every system. Because of this discipline, replacing nuclear fuel became an extremely complicated but carefully controlled operation. The major refueling and modernization process can last almost 4 years. To reach the reactor, engineers must perform something almost unbelievable. They cut enormous technological openings directly into the aircraft carrier's flight deck. Workers remove sections of the massive steel structure. They create access routes through the ship. Then
During the massive refueling process, engineers do much more than replace nuclear fuel. Thousands of pipes may be inspected or replaced. Electrical systems are upgraded. Communication equipment is modernized. New computers are installed. The carrier may receive advanced radar technology and updated military systems. After the work is completed, the enormous openings in the flight deck must be closed. Large sections of steel are permanently welded back into place. Every connection must be carefully inspected. Engineers apply multiple protective layers designed to survive powerful ocean storms. The deck must also withstand the impact of fighter jets weighing more than 30 tons. Aircraft land at extremely high speed. Their landing gear strikes the deck with enormous force. The repaired structure must remain strong enough to survive decades of military operations. And this reveals the real reason why only a few countries can operate nuclear aircraft carriers. Building a reactor is only half of the challenge. The much greater challenge is creating everything required to support it. A country needs enormous dry docks. It needs specialized shipyards.
A nuclear aircraft carrier is not simply a large ship with a reactor installed inside. It is the result of an entire national industrial system. The country must possess advanced nuclear technology. It needs powerful shipbuilding facilities. It requires specialized military engineers. It must maintain secure fuel systems. It needs ports capable of supporting enormous vessels. Every part must work together. A failure in one area can affect the entire project. The reactor must operate safely. The ship must remain stable. The propulsion system must generate enormous power. The electrical network must support advanced military equipment. The flight deck must survive thousands of aircraft operations. The crew must receive years of specialized training. And the ship must remain operational for decades. This is why only a small number of countries have developed nuclear-powered aircraft carriers. The technology is extremely expensive. The engineering is incredibly difficult. And the long-term maintenance requirements are enormous. But once the complicated refueling and modernization process is complete, the giant ship returns to the ocean. The enormous propellers begin rotating again. The steel city slowly leaves the shipyard. It moves silently toward the open sea. For decades, it may operate thousands of kilometers from its home country. It can travel without constantly searching for fuel tankers. It can maintain high speed for long periods. It can launch aircraft far from any land base. And it can support an entire military fleet. The carrier becomes a mobile airfield, a floating command center, a powerful radar platform, and a city powered by a controlled nuclear reaction. But the true strength of this enormous ship is not measured only by the sound of fighter jets launching into the sky. It is not measured only by the size of its flight deck. And it is not measured only by the weapons carried inside its steel hull. Its real power comes from